All right, so today we're going to take a look at conics and calculus. And as we already had talked about before we push play on the button on the screen, conics are the shapes that we actually can achieve when we take a cross-section of cone. And so we're going to talk about three of them today. Specifically, we're going to talk about parabolas, ellipses, and then hyperbolas. So there's going to be a fair bit of writing today with definitions of these items so that we have formulas and pieces of information that we're all using identically. Whoops. All right, so our first one we're going to talk about is the parabolas. This is theorem 10.1. The standard form of the equation of a parabola with vertex HK and directrix y equals k minus p is the following.
Is the left one small k, the right one big K?
It's HK.
Yeah, but
Is the k the same value?
Is this k the same value? Is this the problem? Oh, I think I know what you mean. The k here and the k here. Yes, they're the same value. Sorry about that. Yes, same value. And I'll show you what p is in a minute too, because it gets referenced here in a moment. I'll show you from a visual perspective and from an equation perspective. So one of the equations, there's two equations we're going to have for this. They're really just variations of one another. So x minus h squared equals 4p times y minus k. This is a vertical axis. And so what I mean by a vertical axis, I'll draw them as I go, is that we have a parabola opening, I shouldn't have drawn it quite like that, but we have a parabola opening upward or downward, okay? So it's the standard parabolas that are functions, okay, parabolas that are functions. This point is, of course, called the vertex. And how wide or how narrow the parabola opens is dependent upon the directrix. So the directrix is a line on the side that the parabola is not opening towards. And it's a line that is p units away. All right? That's the p that we see here, and it's the p that we see happening in the equation here. The closer the directrix is to the parabola, the wider the parabola is. The further away, the more narrow. And I'm about to define another term, so I'll just go ahead and draw it in for now, and then I'll define it. There's a point right here, the same distance away. And that point right there is called the focus. Now, so if the directrix is further away, the focus is also further away. They're equidistant from the vertex, right? And the parabola will be really narrow if they're further away, and it will be wide if they're close. Now, we're not going to get too specific on how we're drawing our parabola in terms of its width. That's not what this particular lesson is about. But we will be plotting and finding the vertex, the directrix. Is it a vertical or horizontal? I'm about to do a horizontal one here in a minute. And where the focus is. And we're going to be plotting and graphing and talking about all those details. So this one was a vertical axis. There's also a horizontal axis. So with vertex HK and directrix x equals h minus p, we have this equation. So I still have x minus h associated and y minus k associated, but I switched the location. So I have y minus k squared on the left. In particular, it's squared. And then I have 4p times x minus h. This is not a function, all right? But it is a parabola. It would be a parabola that would be opening either to the left or to the right. And I'll tell you how you know, or can sort of judge pretty quickly whether it opens left, right, similar to how you know whether it opens up or down. So there's my vertex, there would be my focus, and then over here visually would be my directrix. And again, this distance and this distance should be equal. So in particular, the focus is h and k plus p if it's vertical, and h plus p, there we go, and then k if it's horizontal. So rule of thumb, make it super easy for you to remember, or at least somewhat. How do you decide whether a parabola opens up or down? Just think back to what you know about parabolas. What makes that decision? What was it? Yeah, it has to do with positives and negative coefficients of what term? Do you remember? The leading term or the x squared term, exactly. So we've written this in a kind of a funny way, right? But if you take a look at, we'll start with this equation because this is the one that's got the x squared in it. It doesn't even look like there's a coefficient on the left with x, correct? But can you also see how that p right there is the only thing that could make a difference in whether it's positive or negative? But the reality is everything right now is positive. This is squared, so everything on the left side is positive. This piece right here has to do with shifting it up and down, so that it's not opening the direction of it, right? So it's either the 4, which is also positive, or the p, which we don't know, that determines whether it opens up or down. So in particular, if p is positive, it's going to open up. And if p were negative, it would open down. Now it works the same way here. If p is positive, it does one thing, and if p is negative, it does the other. What would you assume, based on what you know about the Cartesian coordinate system? That's right. Positive is to the right, and negative will be to the left. You're going to see a ton of equations in this section. Equations for finding different pieces of information. For the most part, you can do a lot of this graphically. You can do a lot of it with intuition without having a whole slew of equations that you're going to memorize. There's no reason to memorize these last two equations that I just wrote down, finding the focus and the directrix. There's no reason. All you have to do is figure out what p is, and visually you can move things around.
Cartesian coordinates?
What's that?
Are we going to stay in the Cartesian coordinates?
Not later in this section.
Cylindrical?
Yeah, nope, we're going to leave polar coordinates later in chapter 10. Yeah, so, did we hear groaning? You guys don't even know what that is yet, do you? Oh, okay. It's all right, it wasn't you. All right, cool. All right, let's take a look at an example on how we find these pieces of information graphically, because I'm trying to, sort of like pump you up as to the fact that I don't want you to have to memorize a bunch of stuff. So you can see how that would actually work in a problem, okay? So here's an example. We're going to find the vertex. Focus and directrix. And graph. Those are the 4 things we're going to do with our problem. In particular, I'm going to start the problem out with it looking like this, and I'm going to do an example later of how you sort of move things around, a reminder of how you move things around to get them into the form that you would want if it didn't already look like this, okay? So I promise I'll get to that later, but just assume for now that it's sort of partially in a form that you like. Now what we want to do is we want to get it into the form of this previous slide, where I have everything squared on the left and I have everything else on the right. That's my goal. okay? So, on this one, it's the y that's squared, right? So I have y minus 1 squared on the left or right. I don't care where you put it. It means I need to move some other pieces around. So if you think about moving this one over here to make it positive, I would move my negative 4 over here to the x plus 2. So this would be x plus 2. I'm sorry, I had a 4 in front of it. My bad. 4 times x plus 2 and minus 4. It would be positive 4. Thank you. Positive 4. I just shifted a bunch of things. It's all algebra. You guys know how to do that. You're just going to move the x squared to one side or the y squared to one side, whichever one's squared, with its components, and the other pieces on the other side. You can also think about it as isolating all the y's on one side, all the x's, and the constants on the other side. The constants are going to go with whichever terms is not squared. Okay. We do need to clean up the right-hand side just a little bit. This is 4x plus 8 plus 4. What is that? Yeah. It is 12, so it's 4 times x plus 3. Yeah. Ethan knew where I was going. Good job. So, yeah, that is where I want to go. So this is actually now in standard form. Is everybody good with that? Okay. Once we have this in standard form, it will be super helpful if we actually start by identifying p. What is p in this formula, in this form? It's 1, right? The 4 is a part of the standard form of the equation, so it's just 1. So let's actually identify what you can do really quickly. What is the vertex of this parabola? Close. Yeah, negative 3, 1. And in case you're looking at that and going, how did they get that? We're using the coordinates that are beside the x and the y in appropriate order, x then y. Okay, and just like when you do like equations of circles and so forth, it's the opposite sign that you're looking for. So after I found that, I'm going to actually start with the graph. We'll find the other pieces as we go. So here's my graph. I'm going to plot that vertex, negative 3, 1.
Pretty sure it opens to the right.
Okay, hang on a second. I want to do this. Let me see if I can get it to work. Oh, wow, look at that. Isn't that friendly? Not so friendly for the writing part, but... Okay, so
I can't believe you got the lines correct.
the lines happen to be the first time, yeah. Negative 3, 1. There's my point. Wow, technology is so fun when it works out nicely for you, isn't it? So good. Okay, so Ethan says he thinks it opens to the right. What does everybody else think? Yeah, how do you decide?
It's the horizontal form.
Yeah, it's the horizontal form. How did we know it was horizontal form?
Y is squared.
The y is squared. Good job. And then it opens to the right because the p-value is positive. Okay, and the p-value is 1 as well, correct? So where we are right now with our vertex, if I go 1 to the right and 1 to the left, those are going to mark my locations of the other two pieces of information, namely the point of the focus and a point on the directrix. So I'm not done with the directrix, but it does open to the right, like you guys noticed, around the focus that I just put on there, which we'll write the ordered pair for in a moment. And the directrix is going to go through the other point that we just plotted right here. Okay, so we're going to write them down now. So my vertex was negative 3, 1. What is my focus? The focus is an ordered pair. Negative 2, 1, good. And the directrix is not a point. It has a point on it. I mean, I used that as a point of reference. But it's an equation of a line. What is the directrix? Say it louder, Hannah. You got it. It's x equal negative 4. Vertical lines are equations x equals. So x equal negative 4. And nobody needed to use any kind of formulas to find any of that, right? The graph told us what to do when we were looking at the pieces. All right, so this is parabolas. The next one we're going to go to is ellipses. Are you guys ready for that? Of course we are, absolutely. Let's go. Okay. Let me put back my... Where's my lines? There they are. Okay. All right, this is theorem 10.3. Yep, we're skipped one. You can do that when you're the teacher. You can skip stuff. Did you know that?
Skip 10.2?
Yep, skip 10.2. You laugh, but we just did it. Standard equation of an ellipse. (10.2) talked about symmetries, and I think that we could probably be okay with the fact that you guys know what symmetry looks like, right? The parabola, it was symmetric, right? Yeah, it was okay. See, we can skip it, no problem. All right, so here's what we've got. The standard form of an ellipse with center HK. This is the one that I'm doing slightly different than the book, by the way. And major and minor axis of lengths 2A and 2B is the following. Okay, so this is x minus h squared over a squared plus y minus k squared over b squared, and it equals 1. And whichever of a squared or b squared is bigger, is larger, determines the major axis. Okay, so one more piece of information, then I'll actually draw you some pictures. The foci, that's just plural of focus, because there's two of them. The foci lie on the major axis. C units from the center with c squared equal to the absolute value of a squared minus b squared. This is going to look a little different than your book. In particular, C is not defined this way in your book. It does not have the absolute values on it. What your book does is it tries to make it doesn't try, it does. It makes two equations that look almost identical. It just switches whether or not A or B are underneath the X or the Y. Okay? Yes, Ethan?
Is it always a squared minus b squared?
Well, it can be A squared minus B squared or B squared minus A squared. That's why I put absolute values around it. It's just going to be whichever one's positive.
But it's always minus.
Yeah. The plus will be for hyperbolas, and we'll get there in a minute. Yeah, there is a different way we find the foci for hyperbola. Yeah, but it's always subtraction. So really, all those absolute values are doing for us is telling us we're just going to take the larger denominator minus the smaller denominator. That's really it. Okay? So let's take a look at or actually I should show you a picture of these first, and then we'll take a look at an example. So there's two types of ellipses. There's one that would be a vertical ellipse that would look something like this. And then there's one...
Smaller.
Huh?
Larger minus smaller.
Yes. Did I say it backwards?
Yeah.
I'm sorry.
No, the a squared and b squared is messing me up. So it's if I know it's larger minus the smaller.
You can
Then do it that way.
That's all the absolute values.
If you do it with the absolute values, yeah.
Yeah.
So you can do smaller minus larger, and the easiest way for me to convey that was to simply put absolute values around it. That's why I did it that way. But whatever works for you to think about it, it is going to be the larger square, the squaring value minus the smaller one. So these are the two different ways that we can draw an ellipse, okay? One of them is considered a vertical ellipse, the first one, right? Because it's vertically long, if you will. And this one would be a horizontal ellipse. Now there are two axes. There's this one and there's this one. It's the one that's sort of we're going to divide it into, you know, 4 equal shapes basically. Which one do you suppose is the major axis? The longer one. And the minor axis would be the shorter one. And whichever denominator is bigger, if it's underneath x, it's going to be longer in the x direction, the bigger one, right? And if the bigger one is underneath y, it's going to be longer in the y direction. So I don't need to define A and B differently in major and minor axes because the equation itself tells me which one's going to be larger and smaller based on its location. All right? So if I look at it from this perspective, let me just label a few things. Of course, here's your center. We already said this is our major axis. The shorter one would be my minor axis. And there is a value right in here, we'll just eyeball or where we're drawing it, my pink dots. And those are going to be my foci. And you can tell they're equidistant, at least they should sort of look equidistant from the center, by the value c. And c is found by taking the larger of the denominators minus the smaller of the denominators, and then a square root. Okay? Yes, Bryson?
And can you have ever have like a vertical or horizontal like ellipse that is just an ellipse that is like a reflective over the y equals x axis?
So you're thinking about it being more like slanted. Yes, I can't remember if, I haven't gotten far enough in my lesson planning to see if your book is going to address that issue, but the answer is yes, you definitely can. The equations are not nice and neat. They're messy and not super friendly to work with, but yeah, you can, for sure. Mm-hmm.
So for a circle, a squared, b squared are the same.
Yes. Yeah. Everything that you guys know about circles is really just a special case of an ellipse. That's all it is. Yeah, because you'd have ones in those denominators, right? Yeah, or the same number in the denominators wouldn't necessarily have the ones. But yeah. Yep. Okay, I'm not going to mark up the diagram on the left-hand side because it's the same. It just switches where the major and the minor axes are. Is that good? Okay, let's do an example. I mentioned earlier that I was going to do an example that showed you what to do if it wasn't already close enough to the form that you wanted it. Sorry, I have one more definition, so my bad. Let me define this first. The eccentricity, or eccentricity, I don't know which one it is. Eccentricity is the measure of the, I didn't even know this next word was a word, but I'm going to write it down because your book said it's a word, so it's got to be a word. This is the measure of the ovalness. Is that a word? I was pretty surprised. I mean, it's a good descriptor. I just wouldn't have thought it's a real word. The ovalness of an ellipse. It's found by, we call it E, by taking C over A. Now, I kind of left A to be ambiguous, but we'll call A something here now, otherwise it's not going to make any sense. So where A is half the length of the major axis.
The quality of being oval.
Perfect. Did you look it up online?
Yep.
Awesome. So
Other
it
than
is,
that,
in
it
fact, a
gets-
word.
It gets redirected to
It
oval.
does. It gets redirected to oval.
Is E the value of E?
No, it's not. It's just, yeah, this is terrible notation, right?
I'm guessing it's not the speed of light.
No, no. E and C and A here are completely different. E is eccentricity, and C, I'm about to define it, but right now I'm doing A. Half the length of the major axis. And C is the distance from the center to the foci. It's the same C from the previous slide. So visually, let me swipe back over to my other picture so I can show you what the numbers are that you're using. So if you're doing E and C in this diagram on my right, this length in yellow would be A. Okay, it's the half the length part I just described. And C would be this piece in orange, you know, the distance you get to the foci. Okay, so it's a ratio. We're looking at a ratio of these two lengths. Okay, so let's jot down the example next. We're going to find the center, foci, vertices, and eccentricity.
And
Yep.
I may have just tried to miss this, but is the foci supposed to be half the center, half the distance? from
No,
the-
and in general it's not. I think it's only half when it's a circle, if I remember right. So it's a very special case. Find the center of the foci. I didn't actually draw the vertices on my graph, I don't think.
Can
So,
you find the vertices?
yep, you can. The vertices are actually here and here. So they're the end points of the major axis. Those are my vertices. The end points of the minor axis don't have a name. Often we'll find them for reference points as we're drawing it, but they don't have a name. So center, vertices, foci, what else do I have? Oh, eccentricity. And graph. All right, very good. So this one is going to look completely not in a form that's very usable at the moment. X squared minus 4x plus 9y squared equals 5. And I want to pause with you for a moment before we go any further and ask you to describe for me how you know that this is not a parabola. There's two squares. Very good. Now, we're about to enter hyperbolas next, and I need to distinguish with you the difference between the ellipse and the hyperbola. The difference is, for an ellipse, both the squared terms are the same sign. Okay, usually we've got them written, they're both positive, x squared, y squared. When we have a hyperbola in a moment, we'll have squares, an x squared and a y squared, but one of them will be positive and one of them will be negative. There's a portion of your homework where you're asked to decide if it is a parabola, an ellipse, or a hyperbola, and you shouldn't have to go very far down the down the line of doing much with the equation to make that determination. You should be able to look at the signs on the squares and make that determination. Okay, so this is I have ellipse. Blah. Okay, so here's how you do it. You need to have these two pieces squared, and you've done this ages ago. Yes, Ethan?
I'm not sure what to do with the 9, but I do know that there's a -4 that you move to the left.
Okay, so
Can't you just complete the square?
yes, yeah. So we usually encounter this process the first time when we're doing quadratic formula and factoring and stuff like that, and completing a square, and it is going to have a -4 or a +4. We're going to have a 4 involved. And the way that we're going to do it is by isolating the pieces that have x in it versus y. So I chose one that only we had to complete the square one time for, but some of yours you might have to complete the square twice. It's the same process, right? So as I'm completing the square, of course, the goal, is to add or add, it's always add a value right here that will make this a perfect square trinomial. And the way that we do that is we take the middle value, that's -4, and we divide by 2, and then we square it. So what is the middle value divided by 2 and squared? It is 4, +4, you got it. So we've got a 4 right here now, right? Cool, and you can't go just adding a 4, that's not appropriate. You can, or in our case, it would actually be easier to add it to the other side. Yeah, so somewhere you have to compensate. I've chosen to compensate on this particular problem by moving the 4 out. Now, one word of caution. Let's say, for example, that this had 9y squared plus 9y in it, and you were completing the square. you got to factor the 9 out first. You can only do the completing the square with a coefficient of 1 in front of your y squared or your x squared term. So do remember that. That's sort of one of those things that comes up and you're like, wait a minute, it's not working quite right because you probably forgot to factor out the coefficient, okay? So you got to factor out the coefficient to start with. Here's the kicker. This is an ugly one. Let me try a better number here. Let's say it's an 18. So if I have this as, I'm making it up as I go, right? I can do that. So here, let's say that this is a 2y. So if I complete the square, what do I get? It's a plus 1. But the thing that you remember is, say that again, Hannah?
Subtract 9.
Yeah. There's really 9 that you added to the problem, so you're either going to subtract 9 on the same side or add 9 to the other side. You guys remember some of those details?
Yeah.
It's probably been a while. I mean, it's not something we use all the time, but we're definitely going to use it like substantially in this section. Yes, sir?
This is not related to what you're doing right now.
Oh, good.
But I think we're going to divide by 9.
We are. Yes, you are. Okay, so I'm going to actually delete this because it's not related to our problem, but I just wanted to just see what you would do. Yes, okay, so
Isn't that
let's
because
factor
a squared is
this. You guys are way ahead. Slow down. Okay, let's get this done. Are we good with x minus 2 squared?
Yeah.
Awesome. I have 9y squared, and I have equals 9. And the standard form of a hyperbola or a parabola, a hyperbola or an ellipse, is going to have a 1 on the right-hand side. So we need to divide by 9. And beautiful things often happen because, you know, the textbook created the problems for you, and you end up a lot with coefficients canceling out. So that will frequently happen. So I have x minus 2 squared over 9 plus y squared equals 1. This is the standard form for an ellipse. So knowing this now, I think you can probably tell me the vertex pretty quick. Not vertex, center is what I wanted to say. Center. What is the center of this ellipse? 2, 0 is yes, that's correct. Okay, so it's from here and here. There's nothing with the y squared, it's just y squared, so it's 0. So I have 2, 0. Okay, so we're going to fill in all the details, but it'll be easier to fill in all the details if we draw the picture as we go. Well, at least that's my perspective. Okay, I shouldn't have done it that way, but let's try this. Ethan, I was a little off that time, but look, now it's fixed. Just like that. Isn't that fantastic? Okay. Center 2, 0. So we're going to start with the center, which would be here, right? Okay, what is the value being squared underneath the x? Is 9 being squared? It's 3, right? This is a common mistake. That's why I ask it. There's a 3 squared underneath my x minus 2, right? Yeah. So that actually tells me that I'm going to go to the left and to the right because it's underneath x, 3. So we have 1, 2, 3. And I have 1, 2, 3 putting me here. So let's jot that down. Those are my vertices because the 9 underneath there is bigger than the 1 that's underneath the y squared, right? Right. Okay, so my vertices are what? Okay, -1, 0, and 5, 0. All right. What is the value underneath the y squared is a 1 squared, right? So in terms of graphing this thing, I do need to plot that. It's going to go up and down from here, and I'm going to connect these in that ovalish shape, if you will.
Where did the 1 come
I'll show you. Okay, that's not working. It's too narrow.
from?
It's right here.
So that's your minor.
Yep. So that's going to be the minor lengths of the minor axis. Yeah. Yep. Okay, I'm going to try my oval again.
Will we have time for hyperbole?
We found,
Today? I don't know. We'll see.
we found the foci using a c squared.
Yes. Okay, that's pretty decent. So we need to find a foci. That's the last thing here. Well, we haven't found the eccentricity either, but we need the foci to find that, right? So how are we going to find foci?
C squared. Absolute valuation.
Okay, so c squared equals the absolute value of a squared minus b squared. Or you can just remember, like Ethan said, which is honestly how I think about it too. It's the larger denominator minus the smaller one. So it would be
9 minus 1.
9 minus 1. Okay? So c squared is 8. And if I square root, what would I simplify that to? 2 square root of 2. So my foci, and it's going to affect whichever the major axis is. This time, my major axis is the x-axis, right? So this will affect, the 2 square root of 2 will affect the x value from the center. So what was the center's x value? It was 2. So I start with the center's x value, and then I will add or subtract, right? These are 2 points I'm getting, the c value, and then I keep the same y value. So just as a reference point, grab for me. Are you okay, Becca?
Can you say that again?
Yep, I can. So this point right here is coming from the center. It's the x coordinate of the center. And then the 2 square root of 2 is what we just calculated when we were finding the c value.
Okay.
Okay? Very good. And then the y value stays the same from the center.
Wait. Oh, I see.
You good? Okay, somebody grab a calculator. We need an approximation because we're going to plot them anyway. Put a dot on our graph because I don't know 2 square root of 2 out of my head, so sorry about that. You're trying to find eccentricity. You can tell, isn't that what you're supposed to be doing? 2.8. Okay, so that's like about right here. And what's the other one? Wait, was 2.8 your 2 square root of 2? I'm sorry. I misunderstood. Okay, so I need 2 plus that, so it would be 4.8? Okay. So my 4.8 would be right here. And the other one was what? 0.8? I don't think we wrote that down right. Something's wrong.
Yeah, you're supposed to have a negative.
Is it negative 0.8? Oh, okay, that makes more sense. I'm with that. Okay, so it'd be right here. It's like it should be balanced. We should have symmetry going on with those foci. Okay, eccentricity is the last thing to find. Eccentricity is a ratio of c over a. So c would be what we just found, 2 square root of 2.
Not over 3.
Oh, what?
Yeah.
Yes, over the a value, which I told you that was the length right here, right? Was
Oh, no,
over,
it's half the length.
a is half of the whole width of the ellipse.
So why do we have a
So 3.
equals 3 and we have a equals half of 3?
Huh?
Why do we have a equals 3 and then a equals half of 3?
No.
What do you
A
mean?
is 3.
No, a is 3.
Yeah, but then a is half the length.
Ethan, A is the distance from the,
Yeah,
center
so-
point to each of the endpoints of the major axis. So the whole length of the major axis is twice the length.
Yeah, this right here is 2a.
Yeah.
It's 2a to go all the way across. It's a to go halfway.
That major axis.
A is actually
No, it's half. You said half the length of the major. Can we go back to it?
Sure, you bet.
Okay, where a is half the length of the major axis.
Yes.
The major axis is 3.
No, it's not. The major axis in this picture is 6. Okay, because we got to go from the distance from, let me get a different color here. This is my major axis, and that's 6 units long.
Okay.
Okay, half of that is a. That would be the 3 that's showing up underneath the x squared term. Okay? All right, and that one doesn't reduce, so are we all good? Better now? All right, so it's 2 square root 2 over 3.
We just leave it as that.
Yeah. There's really nothing else you can do with it, so you bet we're going to leave it like that. Okay, we're not going to finish the hyperbola, but I am going to start it. Okay, so let me at least define it for you. We'll see if we can get through the definition. And I'm going to give you the homework assignment, not because it's due, because we won't be finished with that either, but that way you can start on it because it's kind of long, because there's a lot going on in this section. What's that face? Oh, come now. You guys know you love math. That's why you're in my class. All right, theorem 10.5, and yes, you're right, we skipped 10.4. All right, this is the standard. It was about symmetry again. Standard equation of a hyperbola. All right, so the standard equation of a hyperbola with center HK is, and we will have two forms for this one. I can't consolidate it, unfortunately. I wish I could. So if x minus h squared over a squared minus y minus k squared over b squared equals 1. Or we have it switched where we have y minus k squared first over a squared minus x minus h squared over b squared equals 1. The first one would be we call it a transverse axis, and I'll show you what that is graphically. The transverse axis is horizontal. And the second one, the transverse axis, is vertical. The vertices are A units from the center and the foci are C units from the center where C squared equals A squared plus B squared. So I'm going to pause with this right here. I'll draw pictures and explain all the details next time, but this is already recorded now in your notes. I'm going to go ahead and write down the homework assignment because you can do the problems related to parabolas and ellipses, and I would encourage you to do that because at some point, just like happened last section, right, last chapter, we're going to get caught up and you're going to have 2 homework assignments due the next class period. So I would encourage you to go ahead and start working on this. WebAssign's not up and running with this yet. I will get that done hopefully later today. So this is page 692, numbers 8, 11, 17, 20, 24, 25, 29, 32, 41, 44, and the last one's 51 through 58, but before you freak out with me, all you're doing for the last ones is identifying, is it a parabola, an ellipse, or a hyperbola from the equation. It's really quick, okay? But you do need to be able to do that. So what can you actually accomplish if you wanted to know what's the minimum that or the maximum I could do today? It's the first 8 problems. So these 8 through 32, and then maybe it's not the first 8, maybe it's the first 6.
I mean, technically we could.
I don't know, something like that. Yeah, there's 2 or 4 of them, I can't remember, that are hyperbola ones. And so just don't do those if you're not comfortable doing that yet, and we'll finish them on Monday.